then go to the video.
Just a moment, let me take the presentation here.
Okay.
I'm Samuel Oliveira,
and
I will present the paper. Use machine learning to estimate latency and delivered packets in a hybrid NOx. Hybrid wireless network on chip are commonly used to ensure trade-off between latency and packet delivery. However, for a good optimization of the NOC, a design space exploration operations indicate to design before performance the hardware synthesis. In a previous work, wired links that interconnect wired and wireless routers are changed to optimize network latency and the number of delivered packets. This operation is done through a genetic approach. However, the design space exploration process performed through simulation tends to be costly, leading us to look for fast solutions that bring the same efficiency. This paper proposes an approach using machine learning to perform design space exploration. Due to the unique nature of a hybrid wired wireless networks, building an effective machine learning model for predict latency and quantify of the delivered packets is challenging. To build the dataset, the data obtained in previous works are used, creating a dataset composed of the characteristics of the networks and the connections of wired links with wireless routers. The topology used is a mesh network, where an order mesh network is composed of the T-routers, which are wired routers. These T-routers are connected through wired links to the innermost mesh composed of H-routers, which are wireless hubs. The experiments are performed with three topology sizes: 4x4, 8x8, and 16x16, alternating injection rate and traffic pattern. In addition, X-ray routing circularity, both with H fleets and X fleet with 32-bit size as with it. The dataset comprises the injection rate used, the traffic pattern, and the connections between wired and wireless routers through the wired links. The dataset also contains information about the latency and quantity of delivered packets to train the model. For the machine learning approach, several machine and deep learning approaches are tested, with the decision tree being the one the best suited the problem in the hand. The training was performed using the tenfold cross-validation technique, where the data set is divided into 10 slots. 9 slots are using the training, leaving space for testing with 1 slot. This process is repeated 10 times, seeking to alternate the batch used for testing in the model. To test the efficiency of the model, the map error was chosen. The results obtained showed that the constructed model could adequately predict the latency and delivered packets values. The results show that larger the topology size, the greater the correctness of the model. The more extends the topology, the more links that connect wired and wireless routers to generating more filters. It's also noted that the model better fits the forecast of the number of delivery packets, probably due the minimal variation, but the values of the quantity of delivery packets in the simulation carry out that make up the data set. The charts show the relationship between actual and predicted values. These charts show the results for the time age topology, and the charts show the results for length delivery packets for the 16x16 topology. The tables show the mean and the standard deviation values obtained for each topology. Show once again that for leg topology, the error rate is low, reaching almost 2% error in some cases. And performing the statistical test, the main test was used. The test show a statistical difference only for the 4x4 and 16x16 topology in both cases. Well, this work proposed a machine learning to build a model to predict network latency and the number of delivered packets. The model takes into account the exchange of wired links that interconnect wired and wireless routers. Data is generated using 3 different topologies plus 3 types of injection rate and traffic patterns. Experiments show that model fits the problem well. In some cases, the difference between simulated and predicted value is less than 2%. The machine learning model obtains the design space exploration result 4,500 times faster than the previous genetic approach. And in the future, we intend to train models for regular hybrid networks and use other evaluation metrics. Thanks, and question, please contact us.
So I thank the authors for the video, for the presentation. I think some of the authors are in the room, Samuel, and I think Monica as well. Is there any question? I suggest the authors to open the camera if it's okay for you.
Hi, Flavio. Here is Leandro. I have a question.
Please, Leandro.
Hello, everyone. My question regards the data sets used in the evaluation. You guys showed in the presentation like a synthetic data set to make your analysis. Have you compared the synthetic data set with real data experimentation to see how similar or how different is that?
Hi, good morning.
Good morning.
The data set was created for experiments. The paper preview present the experiments and the results as used for create the data set in this paper.
Okay. Okay. Just back to my point. It's okay. I think the data set you guys use it. Fine. That's fine. I just would like to know if you had observed real applications and how similar or how different, or it depends on the application, is the data set. Or maybe let me put this in a different way. If I have a certain application, no matter how it is, can I just use, let's say, the adjustments of your network, of your machine learning approach to using my application, or I would need to train it for my according to my own application?
Okay. Her applications get similar results. Okay. According to some experiments performed and is observed.
Okay, I didn't know if I understood you or if you understood me, but I'm okay. We can discuss offline. Thank you.
Thanks.
Thank you, Leandro. One more question, if there's any. Okay, I'm just like to add something to the question from Leandro. You mean real data in the paper? Real mean from a simulator or from a real device? Real devices.
Real simulators.
Okay. So then I'd like to thank again the authors. Unfortunately, we cannot clap hands here. And thank you very much. And then we go to the second paper in the section. The title of the paper is Migration-Based Synchronization. The authors are Stefan Heif, Philipp Hafeck, Luis Gerhorst, Wolfgang Schröder-Preikschat, and Timo Hönig. The authors are from the Friedrich-Alexander University in Erlangen in Germany, and also from Ruhr University in Bochum, Germany. The presenter will be Stefan Heif, and I can see him here in the room. And let's go to the video, please.
Welcome to my presentation of migration-based synchronization, which is a synchronization method for real-time systems that focuses on data locality. When we look at embedded systems nowadays, like, for example, the infotainment system of a car, they are no longer just tiny devices, but they have significant computing performance. And for that, they have powerful processors with multiple cores and a complex memory hierarchy, but they also operate under timing constraints, which are relatively difficult to ensure in a parallel system. So here we see the processor of such a system, with several cores and a memory hierarchy with shared caches and also some core local caches. Let's have a look at a thread that runs on this system. It already has hot caches. Now, if this thread wants to access shared data, it has to take a lock first. Now, it is possible that the lock is free and the thread can quickly continue. However, it is also possible that the lock is taken. Then the thread has to wait, and the lock may even force the thread to sleep. While the thread is sleeping, it is possible that another thread is allowed to run on this specific core, which means that the core local caches lose their state. So when the thread later wakes up, its caches are cold, and it has many cache misses, and it is therefore relatively slow, but it is inside a critical section, which is really bad for the system's performance. So this thread has to reload all data into the first level cache again. Eventually, the caches are hot again, and the thread operates on its data, and also the shared data. When the thread then completes its operation on the shared data, it releases the lock. Then, an access to the shared data becomes forbidden because the thread no longer holds the lock. But the data is still in the level 1 cache. So, effectively, the caches are cold again. When another thread later enters another critical section, it also has to load all data from other caches. So again, caches are cold inside the critical section. So, in summary, data locality is really bad in such a system. There are many cache misses which cause a performance loss. In addition, the cache misses make the timing analysis really difficult. This is particularly bad because synchronization is often performance critical. So, in summary, we have a large execution time and also probably a large overestimation in our analysis. In addition, this problem is likely to become worse over time because the number of processor cores is growing, and then there will be more shared data, which means that there is more synchronization and also more contention. So what we propose to fix this is migration-based synchronization, short MBS, which is a synchronization method that is locality aware. For MBS, we select some processor cores as synchronization cores. These cores are considered an exclusive resource because at any moment in time, at most one thread can run on it. So running on this specific core is equivalent to holding a lock. And to guarantee that this core is indeed an exclusive resource, we only have to disable preemption on this core. So once a thread has access to this core, it remains there until it voluntarily migrates back. So the idea behind the synchronization core is that we can place the shared data in the fast core local caches of the synchronization core. And this data is then considered protected by the synchronization core, which means that an access is only allowed for the thread that currently runs on the synchronization core. So there is no need to ever move this data again because it is only accessible from this one specific core. So when a thread wants to access this data, it has to migrate over to the synchronization core. So we move the thread to its data rather than copying data to the threads. So the benefit is that we always know the location of data, and we can ensure that the thread is always close to its data. Let's have a look at a system that uses MBS. A thread normally runs on a non-synchronization core, which we call application core, as long as it does not access any shared data. And in this example, the thread also needs mutual exclusion to access shared data. Now, what MBS does is to migrate the thread to the synchronization core. So we have to copy the thread and also the top of its stack, but the shared data is already loaded in the level 1 cache of the synchronization core. So when the thread is in the critical section, its caches are always hot. After completing the operation on the shared data, the thread releases the synchronization core, which means that it migrates back to the application core where it came from. So again, we have to copy the thread and also the top of the stack. And afterwards, the thread has hot caches again. In particular, there is no forbidden data in the first level cache. Let's look at the trade-off behind MBS. On the one hand, we have a static overhead, because we lose a processor core just for synchronization purposes. And in addition, we also have an overhead at runtime, which is the thread migration, which is comparable to putting a thread to sleep and waking it up again. On the other hand, we have the benefit of always hot caches, which means that we do not lose any performance to cache misses. And in addition, we can easily analyze the timing of critical sections because we know the location of all data. So we reduce the execution time of critical sections, and we also improve the timing estimations. And indirectly, this also reduces blocking times in the system because the waiting time of a thread for a lock depends on the execution time of critical sections. So basically, the dedicated synchronization core means that we lose a fraction of the available performance, but we also gain some performance due to the hot caches and due to the reduced analysis pessimism. And this trade-off is going to make more and more sense because the number of cores is steadily growing, and then it is much easier to justify the dedicated synchronization core. And also the predictability improvement becomes more important, because otherwise the system could be bottlenecked by slow critical sections and synchronization overhead. One of the nice features of MBS is that it is transparent to traditional logs. First, the migration can be hidden behind a standard interface with log and unlog functions, so there is no difference in application code, just in the log implementation. Second, the scheduler of the synchronization core can apply the same resource assignment policy as the log, such as considering thread priorities, or it can be FIFO or anything else. Finally, timing analysis can also be compatible, because if we keep the original application core reserved, we effectively get the same schedule. The only difference is log holder preemption, which we can have with logs, but we cannot have with MBS. But log holder preemption is not really wanted, because it potentially improves blocking delays, so MBS improves predictability, and in addition, the system analysis benefits from the reduced execution time of critical sections. So we have implemented MBS on two systems to evaluate it. First, we have a soft real-time system which runs Zephyr OS on a Raspberry Pi, and there we analyze the timing with measurements. Second, we have also a hard real-time system with a tri-core processor, where we use a model-based timing analysis that only uses static timing models, and we also use a hybrid approach that combines static models with measurements. On both systems, we run micro-benchmarks, where we access some shared data structures and also some thread-local data structures, which are not contended. So we can adjust the sizes of the data structures, and by this, we can precisely control the amount of data in the caches. So here we see the execution time distributions for MBS and logs for a couple of combinations of data structure sizes. And we see that overall the performance is roughly similar. But in many cases, logs have some latency tail, while MBS has a more constant latency. So MBS does indeed reduce the jitter in the system. And we can confirm that this predictability improvement comes from the improvement in data locality. Here we can see the number of level 2 cache accesses, which occur only when data is not yet in the first level cache. And we see that with MBS, the number of level 1 cache misses, which is the number of level 2 cache accesses, is greatly reduced, at least as long as the data fits the L1 cache. But if the data is too large, then there is no real benefit, as expected. So, in summary, MBS does indeed improve the data locality in the system. And here we see the evaluation of the hard real-time system. We see that without data locality, there is a significant overestimation for both the static and the hybrid approach. However, if we know that data is in the fast core local memory, then the execution time is much faster, and also the analysis is much better, because the timing estimation is lower and also closer to the maximum measured trace. So, in summary, MBS does improve the predictability of the system. This brings me to the end of my presentation. We have seen that in a multi-core real-time system, logs lead to poor data locality. And for this, we have proposed MBS, where all data has a known location in the memory hierarchy. This enables MBS to ensure that caches are always hot and there are very few cache misses. The trade-off behind MBS is a dedicated core for synchronization, but it speeds up all critical sections and also blocking times, And in addition, it improves the predictability of the system. And the predictability improvement can be seen for measurement-based approaches, for entirely static approaches, and also for hybrid approaches. At this point, I want to thank you for your attention, and if you have any questions, feel free to ask.
So thank you, the authors, for the presentation. Questions?
Hi, Flavio. I'd like to make some comments. As far as I understood, you are trading cache misses by migration, but then imagine a scenario that we have lots of small critical sections. You are going to force lots of migrations, so you are going to increase the contention on the bus. And also another question, related question, is that since we are forcing migration of tasks to a single core, I guess you are assuming some kind of particular scheduling policies to make this analysis predictable. And also, I'd like to know whether or not you are considering overloading this synchronizing core. Because if you have lots of tasks to migrate, they are going to compete in the single core for resolving the locks. And then I guess that there might be some point that you have to put another core dedicated to migration and to synchronizing the threads. Thank you very much.
Yeah, just in summary, yes, you are completely right. There is some overhead in migration, and it only really makes sense if you benefit from it. So if you know that you are not going to access a lot of data, then you basically don't really care about data locality. And in that case, it doesn't really make sense to use MBS, but you would probably use some other mechanism. But the general benefit of MBS is that there is this, so you have this trade-off between I have the core and I gain data locality for my entire system. And this might be an issue in your system, and it might also be okay. And the trend is that if you have more and more cores, you probably have more shared data, and you have more contention, and you have more emphasis on making those shared data accesses fast. And then it makes more and more sense to use MBS. But the trade-off point is not really obvious, I would say. So it depends on your data structure. It depends on your access patterns there. It depends on your level 1 cache size. So maybe your data is very small, or maybe it is even too large for the cache. And the trade-off is not really trivial to find there, but in many cases, it already makes sense to use MBS. That is what our evaluation has shown. And there we only had a small number of cores, like maybe 3 to 4 cores. And if you have more cores, it probably makes more sense to use MBS.
Okay, George. We have a question here in the chat from Flavia Maristella. Does it make any difference for your application to deal with homogeneous or heterogeneous multi-core systems? If so, how can you deal with heterogeneous core scenarios?
In our test system, we only had a homogeneous system where every core was the same. Yeah, so I think there are some clever strategies using heterogeneous cores, but we have not implemented them yet. So maybe this is some interesting future work. I think that so you have to differentiate between the type of heterogeneity that you have. If you have, for example, big little, then you can just transparently execute the same code on any core. So it wouldn't really make a difference. But if you have like an ARM core and a RISC-V core, and you migrate your control flow, then you have to compile the program in a specific way. So of course that would be more difficult, and yeah, from a tool chain perspective.
Okay. Any other very quick question?
Hi, me again. Sorry. I'd like to know whether or not you are imposing some constraints on the scheduling policies to be used in your system.
Basically, not really any constraint that comes from MBS, because MBS is more or less just the implementation of the log, and you have a scheduler on the synchronization core. And the scheduler can have any scheduling policy, so you can have it priority-based. For example, then you have a priority-based schedule in your entire system. So basically, you can replace a priority-based log by a priority-based synchronization core. And once you have a scheduling policy in your system, you can just carry it over to MBS.
Thank you.
So then, unfortunately, we don't have more time for questions. You can obviously continue discussing on Mattermost. And I'd like to thank you again, the authors. Unfortunately, I cannot clap hands, but feel yourself clapped. Then we go to the third paper. The title is Performance Monitoring Features in Apples. The authors are Leonardo Horstmann, José Luis Hoffmann, and Antônio Augusto Fröhlich. And they are all from the Software Hardware Integration Lab, Lisha from Federal University of Santa Catarina. Please.
Hello everyone, my name is Leonardo and I'm going to present a work entitled Performance Monitoring Features in Nipples. This work is a collective effort with José Luis Conrad Hoffmann and our advisor, Professor Antônio Augusto Fröhlich, in the Software Hardware Integration Laboratory of the Federal University of Santa Catarina.
Embedded systems, such as the ones adopted in autonomous vehicles, impose an increasing performance demand over modern cyber-physical systems, usually operating with multi-core platforms. Therefore, complex architectural features were necessary to cope with such requirements, such as the utilization of heterogeneous cores, SIMDs, and network-on-chips technology. Yet, the inherent timing constraints of real-time systems and the resource limitation and also shared resources on these platforms make it necessary for us to be able to manage the resource utilization as well as to adapt the platform utilization policy or the models that control the platform, or even to enhance security policies and adapt them during execution. These platforms are highly instrumented and can be monitored and controlled based on the traces they produce during their operation. To do so, it's necessary to build a mechanism that is able to collect runtime data without interfering in the tasks that compose the system, in order to achieve a better and high-quality set of data and also high-quality models. In a previous work, authors have introduced a monitoring framework that is able to collect runtime data without interfering in the execution of the system. In this paper, we investigate 3 different approaches of monitoring and compare their impact on the platform in order to discuss which one is the best sampling method. The monitoring system is part of a scheduling framework that supports the development of domain-specific low-overhead resource schedulers for critical systems. The main constructs of the monitoring system are the monitor and the clerk. The monitor provides the user with a runtime engine to collect data via the clerks. It instruments the scheduler at compile time with sampling operations at predefined points of interest, such as thread dispatches. The data that is captured is automatically time-stamped with high-resolution timers, and the monitor uses contention-free data structures to avoid time-consuming memory operations when storing data. The clerk provides a common interface for the different data sources available on the platform, such as OS variables, hardware counters, and sensors. Moreover, a criterion specification determines monitoring and actuation policies. The periodic monitoring approach consists of periodically interrupting the system execution to perform data acquisition. The interruption period is given by the greatest common divisor of all individual clerk sampling rates. This approach may not scale well for dissonant sampling rates, possibly leading to performance thrashing due to short interruption periods. Other than that, the interruption interference can increase jitter and affect determinism. For a job-based monitoring approach, data is sampled according to the properties of the jobs executing on the platform. For this approach, no period specification is required. Data is accumulated on each context switch, and a sample is triggered at the ending of each job execution. This approach requires individual buffers for each task. However, a lower overhead can be found due to the potentially lower number of captures and also due to the capture operation itself. The execution flow-based monitoring holds characteristics of both periodic and job-based approaches. Here, a data capture is triggered whenever the system execution reaches a point of interest. However, a sample is only collected when respecting a specified maximum sampling rate. The case study for evaluation considers an ARM Cortex-A53 quad-core processor, a processor that holds more than 50 performance events that can be monitored. Also, this is a processor that is widely applied on embedded systems and equips the Raspberry Pi 3B, a single-board computer which will be mediated by EPOS. The goal for our evaluation is to run a synthetic task set that enables representative scenarios for multi-core real-time embedded systems. Moreover, the task set will include scenarios with concurrent architectural usage. In this way, it will allow us to evaluate the overhead of the monitoring system on a broader range of tasks. Three benchmarks compose the task set. The first one is bandwidth, which is a memory-intensive task that periodically performs read and write operations in a data structure with at least the size of the level 2 of the cache. The disparate map simulates a real workload for embedded systems. The workload simulated is used for cruise control, pedestrian tracking, and collision control on autonomous vehicles. The CPU-hungry task performs operations that stress the arithmetical and logic unit. Finally, we use a PDF scheduler with an additional quantum of 100 Hz. The task set configuration is presented at the bottom of the slide.
In this paper, we consider 5 evaluation metrics: system overhead, task overhead, latency, jitter, and memory consumption. System overhead is based on the concept of idle time. We say a core is in idle state whenever it's not executing any system-related operation. Therefore, we say idle time of a system is the time the system is not executing, which means the core is in idle state. In a system with utilization lower than 100%, we expect the idle time to be greater than 0. Thus, when we execute extra operations, in this case monitoring the system, the total system execution time is expected not to be affected if the utilization remains lower than 100%. In this way, we consider the overhead of the monitoring system over the execution of the system as the reduction on the idle time of the system due to the execution of the monitoring approach. Task overhead is considered to be the average impact of the execution of a monitoring approach over the execution time of a task. Thus, the average task overhead is the average execution time of a task when adopting a monitoring approach versus the average execution time of this task with no monitoring approach. The latency of a monitoring approach is considered to be the average time of a sampling operation on this monitoring approach. The jitter for a given approach is considered to be the standard deviation of the time taken by this approach on a sample operation. The evaluation setup considers 10 executions of 30 seconds each, where we monitor 6 performance events and a task identifier, considering 100 Hz frequency for periodic and execution flow approaches. In this way, we can calculate the expected number of samples for each one of the approaches. The periodic approach will capture 100 samples per second on each of the 3 executing cores during 30 seconds of execution, totaling 9,000 samples per execution. It is important to remember that we do not consider core 0, since it is responsible to manage system and control operations, like handling timers and other interruptions, and this will disrupt the timing measures. Similar to that, the execution flow approach will consider the same 9,000 as the maximum number of samples to be captured. On the other hand, the job-based approach will collect data from 6 tasks that execute 2 times each second during 30 seconds of execution, totaling 360 samples. Given this, we can calculate the total memory consumption for each approach, considering a data point or a snapshot as a high-resolution timestamp with 8 bytes, along with the event that's monitored with 8 bytes, totaling 16 bytes per snapshot, and considering the number of channels, number of events that are monitored, and the number of samples that are collected, we can calculate the memory consumption for all 3 methods. The table on the bottom of the slide depicts the total memory consumption for each one of the approaches. To obtain the results for jitter and latency, the execution times collected before and after a data collection in each one of the points of interest. In this way, the difference between the measured times is the time it takes to collect data. So, latency is the average of all the measured times, and the jitter represents the standard deviation of the measured times. It is possible to verify in the table on the bottom of the slide that the latency for the job-based policy was 3 microseconds, while the latency for execution flow was 5 microseconds, and for periodic approach was 6 microseconds. The jitter stays close to 2 microseconds for all the approaches. To obtain the results in terms of overhead, we first calculate the CPU time as the sum of the times of all jobs that run in a certain core during the system execution. Then, we calculate the idle time as a difference from the expected execution time from the CPU time. From these values, we can calculate the system overhead as a difference of the idle time with and without the execution of a monitoring policy. In this way, we can say that the highest impact in terms of system overhead was for the execution flow-based monitoring with 0.28%. Taking into consideration the execution time of each one of the tasks, we can also verify the overhead of the monitoring approaches over each one of the tasks. From this analysis, we conclude that the highest impact was for the periodic approach over the memory-bound task with a 3.47% impact. As one can see, for some of the measures, we found out a negative impact caused by the monitoring approach. As we can see for the overhead per task type, this negative overhead comes from the memory-bound and mid-term tasks. This is caused by interrupting the shared resource contention that happens between these tasks. Anyway, a negative impact still represents an intrusion level over the system, since we change the timing behavior of the tasks. On an overall comparison, we can say that the greatest advantage of the periodic approach is to guarantee sampling determinism, and its greatest flaw is to interrupt the system execution to collect data. The execution flow approach, on the other hand, does not generate any new interruption, and uses non-OS interaction points to collect data. However, this approach does not guarantee determinism on the sampling. Besides, on the experiments conducted in this paper, it demonstrated a fairly close behavior. Meanwhile, the job-based approach presents low memory consumption, around 96% less than the others when comparing for the experiments conducted here. However, it causes an intrinsic loss of the data granularity. Also, this approach does not generate interruptions and performs fewer interactions when compared to the others. We can say that overhead is relative to the number of times the data is collected and also to the operations performed on each data sampling. For the periodic approach, we have on each data sampling the handling of a timer. For the execution flow base, we have on each data sampling a check of a condition. And on the job-based approach, we have two different sampling behaviors, one for accumulation and another for sampling. In this way, we can say that the less intrusive approach in terms of latency is the job-based approach, and the one that presented the minimal jitter is the execution flow-based approach, since it presented the lowest standard deviation for all tasks. Our final remarks are: a careful system design can allow capturing runtime performance data with low interference on the running application. The job-based monitoring approach allows lower memory consumption and overhead. The periodic approach is the more deterministic in terms of periodicity, since both the other approach depends on the execution properties to maintain periodicity. And the execution flow approach presents the lowest jitter. Finally, even granularity problems, such as data quality versus problem domain concerns, is the most impacting factor on the process of choosing between sampling approaches, since the framework demonstrated non-intrusiveness for all of them. An example of that would be on the case of anomaly and intrusion detection. While job-based monitoring could allow us to detect the abnormal behavior while reducing memory consumption and overhead, only with a higher granularity we would be able to detect the exact moment where the abnormal behavior happens. So, here we finish our presentation. Thank you for your attention, and if you have any question, I'll be pleased to answer it.
So, thank the authors for the video. Questions?
Hi, Leonardo. I have a question.
Hi.
I've got your conclusions, but I'm doubt if, let's say, for a given application, if it makes a difference. I mean, should I, as the application designer, select between the three different methods of collecting the data and then compare to realize which is the best one for my application? Or you would recommend in advance, okay, here's the way to go?
It's dependent on the application. And the scenario, for instance, you can have a platform with several limitations, and thus reducing overhead and memory consumption will be necessary, not only important, but necessary. But in case you need, your application needs a periodicity, needs a periodical behavior, guaranteeing a periodical behavior, you may choose another approach. If you need to sample in a higher frequency, but not necessarily periodic, you can use for the execution flow-based approach. You will not generate interruptions on the execution, but we will sample on a higher frequency when compared to the other approach, that is a job-based. If you have a very short jobs, you will also sample in high frequencies, even using the job-based approach. So it's really dependent on the scenario you have, the application, the platform, your limitations, and what you expect from the data you will gather on the execution.
Okay, thank you for your answer. And just another quick question. Do you think that this, let's say, suggestion and this outcome might hold for other operating systems that are not just echoes? For instance, if I try to implement this mechanism on FreeRTOS, do you think I would have more or less the same behavior, or that could be different?
Don't know about the level of intrusion of the other operating system. EPOS is application driven, so it's designed to have a lower intrusion level. So the impact of the monitoring approach should be similar, but they can present different relations between one another because of the OS impacts itself. For instance, the execution flow depends on the operation, the points of interest, the operation points of the OS, the points where the OS interacts with the machine and takes control of the machine, not the application that's executing. So this approach of monitoring, the overhead of it will be dependent on the overhead of the OS. If you have an OS that interrupts more the execution of the system, you will capture more, you will have more overhead. It can present different behaviors.
Okay, thank you very much.
I guess we can discuss 1 minute more if Flavio allows us. Being more technical, Leonardo, because you are here among experts. We have a real-time scheduler which allows us to check how much time we have until the next critical task needs the CPU. So we do much of this monitoring using the idle thread, and the idle thread has a notion of how long will it be running. So how long do I have until the next important event for a critical task? If we can get this notion from FreeRTOS, then the monitoring system itself is accessing PMU, accessing variables, accessing sensors, which are built into the systems. It's not really dependent on EPOS. The key answer would be, if I have this notion of how much time I have until the next critical task needs to run, then I can be mostly safe in telling that we won't disrupt or cause jitter to that task, because we are only doing monitoring inside the idle thread. Theoretically, all systems should give us a notion like that, but in some systems it becomes quite hard to organize things like this. So this would be the point, I guess, isn't it, Leonardo?
Thank you for the input, Guto. I only think that it's very much application dependent, not in the OS itself, but how much time you have in the idle thread. It depends on the application. So you learn, it's more or less if you are running the same application for a long time, so you might be learning from that.
Yes and no. If it's a critical task set, then we are using a traditional real-time scheduler for which we have a schedulability test. Then things get really, really well behaved. And from the parameters of the task, for the schedule, we can calculate. If we use for least laxity first, then we can calculate how much slack we have. Of course, we cannot do monitoring on a system that is 100% used. We need some free slack for the scheduler. But if we are using a classical real-time scheduling algorithm for which we can compute the utilization, then we know for sure, and this is exactly what Leonardo did in this paper. If we have an overutilized system with best effort tasks being canceled, then it's going to be very tough to have this kind of non-intrusive monitoring. We need some slack.
Thank you. Interesting.
Any more questions?
Well, I don't think I have a question because some of the issues were discussed before. But I'd like to congratulate you for the effort, because I think this kind of monitoring will be very necessary for I think, new applications and platform. Since we need to, we are losing predictability in terms of offline design. So I think we need more and more devices and algorithms to monitor the applications, so that we can provide information for better design, even if you consider the system operational. My questions were related to the application that you were targeting, but you discussed this before. Anyway, congratulations for your work.
Thank you.
Taking advantage of my time, sorry, it's fast. How do you compare this with the effort that systems like Perf does in Linux? Is that a big difference in terms of overload?
In terms of effort, in which sense? In terms of performance, or in terms of measuring this performance?
Exactly. Overload that we introduced to monitor the.
I guess when using Linux, perf configuration is a little bit different, right? But I guess isolating the impact of the performance monitoring itself would be a little bit higher in Linux, because you have a much more complex system, right? So isolating the impact of perf would be not so easy than when using a more simple system, because monitor is integrated with the design of the scalar of equals, so it's easier for us to isolate this impact, because we can instrument the monitoring system directly. The perf is a tool that runs along the kernel. It would be much more difficult to isolate the performance.
Thank you.
Unfortunately, we are out of time for additional questions. Then I'd like to thank the authors again, and then we go for the next paper. The title is TRIP, Transparent Resource Provisioning for Multi-Tenant CPU, GPU-based Cloud Environments. The authors are Júlio Costella Vicenzi, Thiago Knost, Michael Guilherme Jordan, Guilherme Corral, Antônio Carlos Schneiderbeck, Matheus Rutzich. All of them are from the Institute of Informatics, Federal University of Rio Grande do Sul. And also from the Federal University of Santa Maria, also in Brazil.
Hello, I'm Júlio Costella Vicenzi, and I'm here to present TRIP, Transparent Resource Provisioning for Multi-Tenant CPU, GPU-based Cloud Environments. Cloud warehouses have been expanding their computational resources with multi-core CPUs and GPUs. These devices exploit parallelism in applications, reducing execution time for tenants and bringing energy benefits for cloud providers. The programming of such applications, however, leads to challenges due to the heterogeneous nature of the system. OpenCL is a framework for the execution of kernels across heterogeneous devices, such as CPUs and GPUs. Here, we see a vector addition example. An API is used for an application to enqueue the kernel to the execution queue of a selected device, such as the CPU. The smallest unit of parallelism in OpenCL is a work item. A work item executes the code in the kernel's body. So, for a vector addition of 100 items, 100 work items are necessary. In a multi-tenant cloud environment, the CPU and GPU are shared. The tenant's applications enqueues its kernels to a fixed device. This can lead to hardware underutilization, leaving certain devices idle that could instead be used in parallel. The programmer is completely responsible for selecting the appropriate device, having no runtime information regarding the availability of resources. We propose TRIP. The framework enables dynamic allocation of tenants' OpenCL kernels to the appropriate devices using a unified execution queue. This transparent abstraction removes the burden of application programmers from having to select the appropriate device for each kernel. It is capable of adapting to different cloud node hardware configurations regarding of CPU or GPU specs. We also present a design space exploration of 5 schedulers: first come, first served, weighted round robin, max min, min min, and first fit. This is our agenda. We'll begin by presenting the TRIP framework. TRIP runs over a multi-tenant OpenStack-based cloud computing system. A cloud node is composed of a single multi-core CPU and a single GPU. OpenCL requests made by tenants are asynchronous and concurrent. This means that the CPU and GPU must be shared between the tenants momentarily. Here is an example of the TRIP framework in action. A unified execution queue is used to receive all tenants' kernel requests. Then, these kernels pass through a scheduling algorithm that will select the best device for execution. The GPU over CPU speedup is an important information used by many scheduling algorithms. For kernels where this information is not available, the kernel work item data is extracted from a request, and the speedup is approximated based on the number of work items, considering that a higher number will mean a higher GPU speedup. Additionally, for kernels that are executed, OpenCL events are used to extract execution time data and calculate this information. This is useful as OpenCL events are native to the API and do not require any additional tooling. However, in this work, we will consider that all kernels are known and this information is readily available for the algorithms. Lastly, each kernel is then allocated to its appropriate device based on the scheduling algorithm. This process is then repeated for additional kernels enqueued by tenants in the future. The framework is capable of processing OpenCL calls without the use of any libraries, application source code modification, or recompilation. This is what gives the transparent aspect of the framework. It is capable of selecting the best target device, either the CPU or GPU, for any given kernel based on a scheduling algorithm. It also stores execution time information to improve forthcoming scheduling processes for certain scheduling algorithms. Now, we will see each different scheduling algorithm available for TRIP. Here we have first come, first served. Notice that blue kernels represent great GPU speedup and yellow ones represent small GPU speedup. Initially, a kernel is enqueued to the GPU, giving it priority. Then, the next one goes to the CPU. Once a device is idle, the next kernel is enqueued to it, and so on, until all kernels in a batch are processed. First come, first served does not use runtime information. However, it does maximize device utilization. This is weighted round robin. For n kernels enqueued to the GPU, one kernel is enqueued to the CPU. In this example, the weight is 2. The weight can be used to estimate how many kernels the GPU is capable of processing by the time the CPU finishes processing a single kernel. If n equals 1, then round robin distributes kernels evenly. In this work, we evaluate round robin with a weight of 3 and a weight of 1. Max-min is the first algorithm that uses GPU over CPU speedup runtime information. First, it sorts the batch in decreasing GPU speedup. This guarantees that the first kernels will make the best use of the GPU. Then, it selects the first n kernels and enqueues them to the device. In this example, we use n equals 3. The remaining kernels with the lowest speedup go to the CPU. As can be seen in the example, it clearly separates the low and high GPU speedups to the appropriate devices, while utilizing both to their capabilities. For the experiments in this work, we use n as 3/4 of the batch size. Min-min is somewhat similar to max-min, in that it sorts kernels in a batch. However, it sorts by increasing GPU speedup. In this case, the first kernels will be the least useful to be executed by the GPU. Then, it enqueues the first n kernels to the CPU. In this example, we have n equals 3. This negative approach makes sure that kernels with low speedup will not be enqueued to the device that is not appropriate. For experiments, n equals 2/5 of the batch length. First fit is the last algorithm, and it is much more straightforward. Any kernel with a speedup higher than a given n is enqueued to the GPU. Then the remaining kernels are enqueued to the CPU. This means that if a batch that greatly utilizes the GPU might avoid CPU execution altogether, leaving the device idle. This, however, ensures that kernels executed by the GPU meet a minimum criteria, making sure that the hardware is properly utilized. Now, let's see the methodology. Polybench is used to evaluate the framework. The 18 kernels are classified considering the amount of data transferred to each device memory, GPU speedup over CPU, and CPU execution time. Using these characteristics, we then form batches with kernels with high values, small values, and mixed scenarios with high and small values. Additionally, a scenario with all available kernels is also formed. Here, we see the different kernels that composed each of the 10 different execution scenarios, as well as their abbreviation that will be referenced in the results section. 3 different execution environments are used to evaluate the framework, always with an Intel Xeon Haswell processor along with an NVIDIA GPU. A Tesla K20M being the least powerful, a Tesla K80 being the medium powerful, and a GeForce GTX 1080 Ti being the best GPU. Let's now discuss results. Here we present makespan and system energy for NVIDIA Tesla K20M. The makespan considers the time used by the last device to finish execution, and system energy considers the sum of both devices. For these results, the smaller the value, the better. We see here only CPU and GPU execution. The exclusive GPU execution is used as a baseline for comparison to other trip algorithms. First come first served achieves a 1.23 speedup on average, being the best result for the S- scenario, and significantly worse in the S+ scenario. Additionally, energy consumption increases by 28% on average. This is due to the fact of the use of 2 distinct devices without significant time speedup, consuming much more energy. Neither round-robin nor weighted round-robin achieve any significant speedups in terms of makespan, and they actually cause performance penalties of 18 and 14%. Additionally, an energy consumption of 42% and 42% is increased. This is due to the fact that they are very naive algorithms. They don't have any information regarding the runtime environment or the availability of devices. Max-min and min-min achieve significant results, being the best in the following scenarios. With up to 5.7 times speed up and 60% energy savings, they also struggle in the S- and S+ scenarios, alongside the other algorithms. Overall, a 24% energy savings is gained by using these algorithms. FirstFit achieves the best results in the following scenarios, with up to 8.35 times speedup. And in terms of energy savings, these are the best scenarios, with up to 75% energy savings. Additionally, it achieves 3.96 times speedup on average, with no performance penalties in any scenario, as well as 36% energy savings. This is the execution timeline for the scenarios with the highest and lowest GPU speedups. As seen by the first-come, first-served algorithm, any kernel allocated to the CPU will cause a significant slowdown. This is why so many algorithms struggle with these scenarios. Differently, in the S- scenario, first-come, first-served does achieve a small speedup. However, this leads to an increase of energy of 30%. Therefore, in both of these scenarios, the best allocation is only GPU and only CPU. And the algorithm that can achieve this allocation is only FirstFit. Here are results for the Tesla K80. Round-robin, weighted round-robin, and first-come, first-served still lead to performance penalties. Max-min and min-min achieve 2.6 times speedup on average and 19 and 17% energy savings. However, they still suffer performance penalties in the S+ scenario. FirstFit continues to achieve great speedup with 3 times on average with no penalties and 33% energy savings on average. Similarly, NVIDIA GeForce 1080 Ti achieves significant speedup for max-min and min-min, with 3.8 and 3.5 speedup on average and 24% energy savings. However, in the S+ scenarios, there is still performance penalties. For FirstFit, no performance penalties achieved, and a 3.8 speedup on average, with 33% energy savings. Here, we see the summary of our results. The framework is capable of achieving on average up to 3.8 times speedup and up to 36% energy savings. It also is capable of adapting for any different hardware configuration we've evaluated. And finally, conclusion and future work. I presented TRIP, a framework to schedule OpenCL kernels transparently in a CPU-GPU multi-tenant cloud node, optimizing make, span, and energy. FirstFit is the standout scheduling algorithm. As future works, the estimation of acceleration of unknown kernels is an interesting problem. As well, varying computational loads can be explored when you consider max-min, min-min, and FirstFit schedulers. Thank you all for your attention.
Thank you, the authors, for the videos. Any questions? I have one question. It was not clear for me how the approach is really transparent for the user, for the programmer, in terms of code generation for different devices, for example. I think you didn't explore it in the previous, if I'm correct.
Right. The framework actually doesn't generate code. What it does, it schedules the kernels to each device. And in OpenCL, you actually compile code before executing the kernel. So for example, if you have a GPU, you compile it and then you execute it. So you can execute the code for the CPU or the GPU, and you do the compilation before execution. This is generally how applications handle the heterogeneous architectures, right?
But if you want to make the approach transparent for the user, you would have to compile it beforehand for different devices. Is it correct?
Yes. So yes, you do need to compile it before execution. And like I said, this is generally how OpenCL applications work. So you need to do that anyways, right?
Any more questions? So then I would like to thank the authors for the paper. And then we move to the final paper in this session.
Thank you.
It is on the selection of relevant hardware events for explaining execution time behavior. The authors are Tadeu Andrade, Jorge Lima, Veronica Lima, Viviana Cucu-Grosjean, and Yasmina Abdedaim. Sorry if it's not the correct pronunciation of the name. The authors are from the Federal University of Bahia and also from INRIA, Paris, from the Copernic Research Group.
Hi, my name is Tadeu Nogueira, and the title of your papers is on the selection of relevant hardware events for explaining execution time behavior. Current architectures use important components that are helping increasing system performance, such as pipeline, branch prediction, multi-core processors, and cache memory. However, they bring considerable challenge to predictable real-time systems due to randomness presented by some of the components, such as cache memory. For these architectures, measurement-based time analysis, MBTA, is a more tractable option. The MBTA estimates the upper bound of execution time using data measuring in different scenarios. In this context, it's important to understand what kind of interference the task is sensitive to. These architectures contain performance monitoring units, PMU, capable of counting hardware-level event occurrences, such as cache and branch predictions. This information is essential and can help you understand the timing of tasks. The type and number of counters vary from architectures to architectures. The number of PMU registers is limited, making it impossible to count all events simultaneously. The use of PMU has been applied in different proposals, such as performance improvement, operating system evaluations, malicious attack analysis. And MBTA, its use is not that common, as its main goal is development model based only in measuring execution time. A close approach to it is present by Griffin. In his work, his groups events using PCA. In our case, you select the most relevant events. Objective. In this work, we present an approach to select the hardware events that are most relevant to explain the runtime behavior of a task. 1. We monitor the task for two different scenarios, baseline scenario and the stress scenario. The stress scenario is configured to induce cache and memory access interference. 2. We perform an event classifications, checking which events best explain the execution time behavior. For this, we used the statistical equation Z0 and F0. Based on comparisons of mean and variance between two distributions, we used the 15 Malardale benchmark. 3. We apply multiple linear regression to predict the task execution time and compare with the observed execution time. 4. We check the quality of the selection of events. We are first comparing prediction using select events with events related to cache miss and branch prediction. Afterward, we used the same events in architectures without operating system, but inducing cache and memory access interferences. Methodology. We use a Raspberry Pi 3B with an ARM Cortex a 15-tree processors, 1 GB of RAM, and a 2-level cache, 7 event counters, and 59 hardware events that can be counted. One counter we use it to number of cycles. In our approach, we use one counter for count execution instruction. Therefore, there are 5 counters left for the older events. Inspecting the 59 hardware events, some had constant or null values. We consider that these events are yellow events to the research. Also, some events contain other. In this case, we consider the most general event. In the end, we are left with 20 events shown in this table. We highlight here the last 6 events. These events represent the number of cycles the CPU waits for a specific condition. To monitor events, we use a Perfect Event Open interface present in Linux operating system. Here is a simple example of the tracking code. To induce interference in the stress scenario, we used the program of the Michael Battle and Ian. Used in the research to check security issues related to cache. We run this program on core 1, 2, and 3. The task we are measuring is run on core 0. Here are the tasks we looked. The table shows a significant variation in the number of instructions when used random inputs. Having bubble sort with the most significant number of instructions and binary search with the last number of instructions. We want to look at how much the events change from baseline scenario to stress scenario. If the event has a significant variation, and can be a good candidate to explain the execution time. To produce a classification of events, we need to analyze all events for both scenarios. Since we have 5 available counters, we run the events every 5. Each group of 5 is performed the 1000th times. So, we have 14,000 to run for the baseline scenario and 14,000 for the stress scenario, totaling 18,000 execution per task. We use equations Z0 and F0 to compare the mean and variance between events. In the formula, EY1 represents the events variance for the stress scenario and EY2 the average for the baseline scenario. SY1 squared the event variance in the stress scenario and SY2 squared the event variance in the baseline scenario. We then ordered the events in the descending order of relevance. We selected the first 5 events. If there are selected events that are correlated, we replace the worst ranked correlated event with the next event from the list. The final list of selected events is in this table. The event E7, interruption at stage right of the pipeline due to a cache miss, was selected in the algorithm for the bar equations Z0 and F0. To check the quality of the selection, we compare the result of the linear regression using the Z0 and F0 selection with the result of the linear regression using the events 0x01 L1I cache miss, 0x03 L1D cache miss, 0x17 L2 cache miss, 0x10 branch miss prediction, and 0x12 branch prediction executed. We chose these events because a lot of work has used on a cache miss and branch prediction as the main cause of the randomness. We quote some references in the paper. Then, we applied the events selected by Z0 and F0 in a stressful environment, but adopt an operating system. We call this environment bare metal. We can represent the execution time Tn equals an plus b, where n is the number of instructions and n, a, and b are greater than 0. The longer the execution of the algorithm, the more the algorithm benefits components such as cache. A and b are random variables that we cannot measure directly. These are manifestations of the execution environment. Thus, the events we collect may be able to measure approximate A and B, as the number of instructions can potentiate the manifestation of events. We normalize the formula by instruction. So we are left with Tn divided by n equals A plus b divided by n. We call Tn divided by n of the pace or Pn. So we can set up the following multiple linear regression: x1 to x5 are the event values normalized by instruction. Some aspects affect your model, such as limited number of counters, negligence of the type of instruction, possible bit of measuring errors. We collect the dosage data for which algorithm in which scenario using random inputs. 75% of the data we use it for model estimation and 25% for checking model quality. We use the mean error to calculate the prediction error. In the formula, this pi is the observed value, and this is predictor value. AVGE represents the mean error of the observations. Here is the result of the algorithm for the two scenarios. CB represents selection with events related to branch prediction and cache memory. Bare metal represents an environment similar to the stress environment, but without operating system interferences. In all situations, the result of Z0 and F0 for the bare metal environment was acceptable. In all algorithms, the average error of Z0 and F0 was less than or equals to CB. This graphic shows the prediction result for the bubble sort using the Z0 selection. The y-axis represents the observed values and the x-axis the predicted values. The red line represents as perfect prediction, with the predicted value equals the observed values. We can see that for the interference environment, the events used in CB had poor predictions. For Z0, the prediction is acceptable for the various scenarios. In this graph, we have the result of the prediction for binary search. CB events present poor prediction for the base scenario and the stress scenario. The F0 selection presents a reasonable result for the two scenarios. We realized that the longer the execution time, the better the pace prediction. In the figure, we have an analysis of the recussion algorithm. The first graph is the observed value by predicted value for Z0 events. The second graph is the error analysis by instruction. The error value is greater when the number of instructions is close to 0. The third graph is an approximation of the last point to the right of the second graph. There is a variation in the error, but the errors are so small that it looks like a single dot. The effect of B divided by N depends on the analyzed program. For recursion, the values of N must be larger to compensate for the variation in B, while for binary search, the small values of N simply suffice. Conclusion: we described an approach to select the hardware events that are most relevant to explain the program execution time. To check the quality, we used multiple linear regression. We showed that the selection process can be used to predict the expected number of cycles divided by instruction with an acceptable level of precision. Hardware-level events occurrences can be used as additional information for techniques such as MBTA. Integrating execution pace information into the MBTA is the next challenge we will face. Thank you.
Thank you, the authors, for the video. Questions?
Hi, Flávio. Hi, Jorge. Hi. Let me address a question for you guys. So, assuming I have, let's say, one application that I want to analyze using this technique. So I must put it to run and use a sort of monitor to cap the PMU instructions. It's like the similar monitor than presented by authors from Lisha and Guto that should be running together with my application to collect the events. Or should I, or on the other hand, or I can run the program on a CPU simulator like the Gem5 simulator that, by the way, we are going to present this afternoon. So what would be the direction?
Hi, Leandro. Thanks for the question. Well, you can do both, but the reasoning for this study was the following. In the real-time system community, we are used to seeing people measuring cycles and then making predictions about the execution time bound. And also we see that lots of studies put cache misses penalties to account for some kind of extra time to deal with these penalties. But in the multiprocessor environment, doing this kind of thing is not trivial. So we start to investigate how the hardware occurrences of these events actually impact the execution time. So we actually did a very simple thing. We measured the events, but then we had to select some because we didn't have enough PMU registers to see all at once. And then we followed those methodology to select events. And amazingly, the predictions were quite precise using a very simple linear model to do so. In previous stage of our study, we use the simulator, but the simulator is quite a controlled environment, and we don't see much error in the predictions. So we moved to a real environment to see that. And yes, you can use in the simulator, but there is no benefit because we don't have any much source of error. You control everything. You measure everything perfectly, and actually you put the penalty you want to see. So it's a kind of a well-behaved random variable to speak of.
Yeah. But it's a very interesting work. Congratulations for you in name of our authors.
Thank you very much.
We have a question here in the chat from Flavia Maristella. I have a simple question. I don't know if I missed anything, but the system model assumes independent tasks.
Actually, assumes just one task that we are analyzing. We're just monitoring one task. We run this task thousands of times to get sample the events and the execution time, introducing source of variations like introducing access to the memory and cache. And so it's just a simple task. But we have lots of tasks related to the operating system that are concurrently there. And we have also an extra task in some scenarios that we call stress scenarios that we use to induce the interference that we would like to see how those interferences actually affect the task that we're monitoring. So there is no inference made for concurrent tasks like sharing memory, having critical sections, or this kind of thing. The intention is to bound the execution time for a single task. So we have to start each task at once.
Okay, Flavia. Any more questions? I'd like to make a simple question. I think you have concentrated on average cases. Probably for a specific application, you could also analyze the worst case scenarios or best case in worst case.
Actually, we are considering the average case to stack the model. Okay, but I don't know if you remember the graph that have a straight line. Those graphs say basically the thing. The speed of the execution follows a line. The more events that affect the execution of a task, the higher the execution time is. But and also it follows the higher, then more instructions to execute also will affect linearly, on average, the execution time. So we put all together and verified that that's true. So I think we can extrapolate somehow. We didn't use in this paper, forget the bound of execution time. This was not the goal of this work, but we are going into this direction right now, using this information that we know now, and to see how to bound the execution time in the worst case.
So, thank you very much. We are ahead of time. Unfortunately, we don't have more time for questions. And I would like to thank the authors of this last paper, and we conclude here this session. I'd like to thank all the authors again, the attendees, and also Leonardo for helping us with the support during this session. And thank you very much.